So we had just started talking about 2.4. Last time we had looked at, different types of examples on, how to do these addition, subtraction, multiplication, division. And then we had briefly talked about, um, how to work with the domain of these functions. So I wanted to look at just a few more examples from 2.4. So let's take a look at this example over here. So this one, the example we had done last time had used a set of ordered pairs for our f and g function. And this one is going to be, of course, in form of an equation. So they're asking us to define what g divided by f is going to look like as a function, and then, of course, find its domain. So when they are giving us g over f, of course, by using the definition for these operations, you can basically see when we have g divided by f, you know what, hold on a second. Let's do this over here. So g divided by f of x basically means you're taking the g function on the top, dividing it by the f function on the bottom. So of course you can see the g function is defined as x minus 19. So that will go on the numerator. The x function is defined as square root of x. So of course that will go on the denominator. So that's basically what you are doing when they say come up with the equation defining g over f. Okay, let's see, that was mission. Alrighty. So my MATLAB actually just wants you to come up with, this definition for our function. I don't think they really want us to simplify or anything like that. So we should be able to go ahead and just type this answer in. So that would be x minus 19 on the numerator. And then we are dividing that by square root of x on the denominator. All right, so now that we know what the g over f function is going to end up looking like, can somebody tell me what do you think the domain for this function will be? So again, the first thing you want to do is, start out by thinking what the domain of each of these individual functions is going to look like. So what is going to be the domain for the f function? What's going to be the domain for the g function? And again, if you remember from our handout over here, we had talked about this. Whenever we are looking at, these functions with the addition, subtraction, multiplication, division, we talk about those domains being the intersection of the domain of each individual function, f and g. And, of course, when it comes to the division function, you want to make sure none of the numbers we are using are going to make the function on the denominator a 0. So that's the idea we want to use over here is, so we look at the domain of each individual function. We talk about what that intersection would look like. And then, of course, that will lead us to what we think the domain of the g over f function is going to end up looking like. So can somebody tell me what the domain for just the f function is going to look like, the square root of x function? Go on. So what do you think the domain for the square root of x will be? What kind of x values can we use in that?
Would it be all numbers greater than or equal to 0?
Very nice, Allison. Yeah, because remember, with the square root of x, we cannot have any negative numbers in there because that's when we start looking at imaginary numbers. So very nice. When we talk about the domain for a square root of x function, you can have 0 or all numbers greater than 0. All right, very nice. So in that same way, what do we think the domain for the g function would be? X minus 19.
That one's just all real numbers, right?
Yeah, very nice, Teddy, because we have no restrictions. We don't have to worry about, anything not working for our x variable, so all real numbers. So now if you think about the intersection between those two domains, of course, the intersection would be starting at 0 and going to infinity. So the idea is whatever we are seeing in the intersection, can we use the same values in the domain for our g divided by f function or g over f function? Or do we need to modify it?
Wouldn't we modify it?
Okay, so what would you do for that, Teddy?
Would it then be 0 to positive infinity?
Okay. So how are we modifying it? Because right now you're saying the same thing, right? 0 to infinity?
I mean, we need to change the 0 to a circular
Parentheses.
parentheses. That's what it is.
Okay, and you want to tell me the reason why we are changing it from a bracket to a parentheses? What are you kind of thinking in that sense?
Honestly, I kind of forgot. I'm just looking at my notes right now.
Okay. Okay, so can somebody else tell me why we don't want to include 0 in our domain for the g over f function? What will happen if you include 0?
The denominator would be 0.
Yeah, very nice, Michelle. Exactly, because if you make your x value become 0, you would end up getting 0 minus 19 on the top and then square root of 0 on the bottom. And of course, you can see that would end up giving us division by 0, which is of course going to be undefined. So that's the reason why you do not want to include 0 in your domain. So when we write the domain for the g over f function, it's still going to go from 0 to infinity, but not including 0. Because technically the idea is you can use 0.000001 and that's going to be okay, but just the number 0 itself is of course making our denominator become a 0, which would be undefined. So that's the modification we're going to have to do over here. So let's go ahead and type that in. So that would be 0 to infinity. Okay, and of course, not including 0. So check our answer, and that is good. All right, good job, guys. Okay, so that was one example for us to see how the domain and range would work out, based on equations instead of a set of ordered pairs. So let's look at our next example over here. And this is actually where we are getting into the composition of functions. So that's the next part in this section that we want to talk about. So, when we're talking about composition of functions, we're basically saying that you are taking two functions and you're composing them together, which basically means we're actually going to take one function and put it inside of the other function. So in addition, subtraction, multiplication, division, we were just taking the two individual functions and doing those operations. Here, you're actually going to take one function and insert it into the other one, which will again, obviously help us create a new function. So just as the notation for composition over here, you should notice that we are using this little open circle. So that looks a little bit different than multiplication, and you can kind of see that over here. Multiplication, we would of course just go ahead and multiply the two functions together. But when we're talking about composition, like I said, you're taking one function and putting it inside of the other function. And this little illustration kind of, neatly shows you how that happens. So you first start with the x value, you put it, inside of the inner function. Whatever answer you get from that, you're going to put it inside of the outside function. So basically, if I give you the order as f of g, that means f is going to be the outside function, g is going to be the inside function. So the way these calculations, I guess, work out, and again, guys, you should have seen the video lecture for this, so I hope you're kind of aware of that. But when they are giving us f of g of 6, basically that means f is, of course, you can see the outside function, g is the inside function. So when they're asking us to simplify this, there we go. The first thing we are going to do is get the inside function to solve. Not sure what's going on. So f on the outside, g of 6 on the inside. So first, we are going to simplify g of 6. So let's do that here on the side. G of 6, that of course means you are going to the g function and you're replacing your x value with number 6. So what do you think that answer will come out to be for the g of 6? Dalton, very nice. Yeah, because you're going to have x squared, which will of course end up becoming 6 squared plus 1. So that would be 36 plus 1, which of course ends up giving us 37. Hey, Daisy, is it possible for you to maybe move around a little where you might have a stronger internet connection? Or do you think it's going to be the same? I'm not sure if she can actually hear me. I might have to message her. All right, guys, so just very quickly while I can go and help Daisy over here. So basically you can see when we simplify that g of 6, we end up getting the inside answer is now going to end up becoming 37. So you're replacing g of 6 with 37. And now for f of 37, of course, we go back to the f function, and now you're going to replace the x with 37. So what will that answer come out to be? Okay, Noah, Allison, you guys have negative 112. Alrighty, so you've got negative 3. X will, of course, become 37. And then you are doing minus 1. So let's see, this will end up giving us negative 111 minus 1. So yeah, very nice. That is where we are getting our negative 112 for. So the way these guys work is, of course, you can see initially we started out with 6 as our x value when we first started solving this. So by the time we solved it through the g and the f functions, the very final answer came out to be negative 112. So that's kind of how these ordered pairs would end up looking like. Of course, they're not asking you to type in an ordered pair for your function here. You're just putting the final answer, which would be our negative 112. Alrighty. Did anybody have questions on this one? I'm not seeing anything. And Maciel, I just saw your answer also for that as a negative 112. All right, very nice. Now let's take a look at this guy over here, very similar, but now you are doing 3 functions instead of just 2. So we've got g of h of f at 3. So this guy, when you are writing it out, of course, that means G is going to be the outermost function, H is going to be in the middle, and then F is going to be the innermost function, and we're starting out with 3 for the F function. So you're going to do F of 3 first, again, like we did in the previous example. So what do you think F of 3 will come out to be? Alrighty, Dalton, you've got 11. So again, guys, this will be 6 times 3. And then we subtract 7 from it. So of course, that's going to be, Teddy, you got the same thing, 11. You're doing 18 minus 7, you know, which will of course end up giving us 11 as the answer. All right, very nice. So that means now we will have G on the outside, H in the middle, and instead of F of 3, you know, of course, we will replace that with 11. So that means now we need to simplify H of 11. So that will be our next step. So again, guys, what do we think H of 11 will come out to be? So H of 11. Okay, Teddy, you've got 117 in there as one of your answers. And then Dalton, you came up with 3. Noah and Allison, 3. Maka, you also have 3. Okay, very
Yeah,
nice.
I think I did something wrong.
Oh, okay, I see. Okay, yeah, I was wondering where you're getting that number from. So let's see, Michelle, Kalia, you guys also have 3. So, you know, of course, we are taking that number 11 for our X value. You're adding 7 to it and then dividing that by 6. So you can kind of see we're almost undoing what the F function did. So you would end up with 18 divided by 6, you know, which would of course lead us to that answer of 3. So again, we come back to our original function here. And now we have G on the outside. And instead of H of 11 now, you're replacing that with 3, which will of course bring us to the G function. So when we plug that in, what do we end up with as our final answer here?
So I actually did the G function instead of the F function on, or no, the H
That's
function on that one. So that's
why.
what I did wrong.
Okay. All right, let me see. Dalton, Noah, Allison, Maciel, Raylan, Kalia, you guys have 5. Yeah, because that's going to be x squared minus 9, which would of course be 3 squared. Sorry, minus 4. 3 squared would be 9, and 9 minus 4 would definitely end up giving us 5. All right, Jacob, you also had that. Very nice. So in this case, again, guys, you will see initially our X value that we started out with at the very beginning was a 3. And then by the time we did all 3 of those functions, you know, we're coming up with 5 as our final answer. So again, they are only asking us to type in the final answer. So you're only, you know, of course, looking into plug this in, and that will be our 5. And that should work. Alrighty, very nice. So just, you know, to show you how these different composition of functions kind of work out in our case. So let's take a look at one more type of question with these compositions, but this guy looks just a little bit different. So you can see they are saying use the 2 given functions to write y as a function of x, because if you look at the way the functions are given to us right now, y is actually in terms of w, right? So this would be y in terms of w. So y is right now in terms of w, and they're asking us to write this as y in terms of x. So what's going to happen is you would have to, go from y in terms of w, which is what we are given. And then you can see w is actually given to us in terms of x. So you would have to go from y to w to x to come up with that. So what this will actually involve is basically, we are going to take this definition for w, which is x plus 6, and you're going to have to substitute that inside the w, in the y function. So you're going to have to make that substitution over here. So we are given y equals w squared minus 1, but then instead of w, you are replacing it with, x plus 6 from that second equation. So it's still a composition function, but they're giving it to you more in terms of, y equals w squared minus 1. So y in terms of w in terms of x. So how do you make that happen? So go ahead and simplify this and let me see what you come up with as your answer. So take a minute, don't send your answer in just yet. Let me see what answers you are coming up with. All right, go ahead and send it in, guys. All right, so you've got x squared plus 12x plus 35, x squared 12x 35, x squared plus 37, x squared 12x 35, x squared 12x 35, okay. X squared plus 35, x squared equals 12x plus 35, okay. So, of course, when you are seeing this expression, x plus 6 in the parentheses with the second, oh, okay, Teddy, got it. That should be a plus sign. So, of course, the first thing we are going to do is, we need to FOIL this x plus 6 squared. So let's go ahead and do that first. So that means we are taking x plus 6 and multiplying it to itself. So when you do the FOIL, you will end up getting x squared. 6 plus 6 will add up to 12x. And of course, 6 times 6 will give us 36. So when we come back to our problem over here, you will end up with x squared plus 12x plus 36. And that minus 1, when you combine those terms together, that's where that 35 is coming from. So it looks like Chloe and Michelle, you guys ended up missing that middle term in there. So yeah, this guy should be y equals x squared plus 12x plus 35. And looks like Jacob, you also missed your middle term in there. Maka, you have x squared plus 12x plus 35. All right, so let's go ahead and put this answer in. So we have x squared plus 12x plus 35. All righty, there we go. Did anybody have questions on this? So those of you who missed the middle term, I think what happened was you just ended up squaring the x squared and the 6, right? You did not do the entire FOIL. So just be careful about that, because anytime you have two terms inside the parentheses with the square outside, we definitely want to use FOIL to multiply them. Alrighty, guys. So you of course have a couple different types of examples in here that we did not go over. So I would like you guys to try that on your own. And again, if you get stuck on anything, you can definitely come to me for help. So that's kind of, you've got different types of examples that I have in here that you can kind of look through with the video lecture. But let's get into our inverse function, section 2.5. So when we're talking about inverse functions, basically we're talking about what one function will do, the inverse function will undo. So if you just think about, functions like addition and subtraction, whatever the subtraction function is doing, the addition is undoing that, or vice versa. You can think of, how division will undo what a multiplication does, or for that matter, how a square will undo what a square root function does. So basically that's what we mean by inverse functions. But of course we know we have more complex functions than just one operation that's happening, because you can have addition, multiplication, and square root happening within the same function. So then how would we create its inverse function? What would that inverse function look like? So that's kind of what we're talking about here in this section. So again, you should have seen the video lecture for this, but basically the idea is if we are ever going to find an inverse function, we have to make sure that function is one-to-one, which means the correspondence between our two variables, x and y, has to be a one-to-one correspondence. So the idea here is, when I'm talking about the one-to-one correspondence, we're basically saying in a function, you cannot have two ordered pairs where, you will have different first coordinates and the same second coordinate. So basically we're saying for different x values, you should not have the same y value, basically. Because if you have, this happening where you have the same y value with different x values, that means we do not have a one-to-one correspondence. So you can kind of look at the pizza example that we have here. You can see for a given dollar amount, we have a specific number of toppings. So if you're paying $13 for pizza, we know we're getting exactly 4 toppings. So it's not like you can have 4 toppings on a pizza, but then you can pay $13 or, $17 and you still get only 4 toppings. That would be a not one-to-one correspondence. So for $1 amount, there's one, topping, how many toppings you're going to have. The other thing is, if we do have this one-to-one correspondence, you can see how we can actually switch those x and y values. So in the first table, we're using x as the dollar amount, y as the number of toppings. And then you can see in the second table over here, we're switching that and we have x as the number of toppings and y as the dollar amount. So what happens here, guys? The first table, you can think of that as the original function. The second table is actually its inverse. So just by switching our x and y variables, we are able to create the inverse function. And this only happens if we can show that our functions are one-to-one, that we have that one-to-one correspondence between our variables. For a contrast, think about the dollar menu at a fast food restaurant, Taco Bell, Wendy's, whatever else is out there. For $1, a lot of these places will give you like a drink, maybe a fries of certain size, a burger, maybe a wrap, or something like that. So you can see for the same dollar amount, we can have 4 or 5 different menu options. So that is not a one-to-one correspondence, because I have the same dollar amount on all of those. So there is not that unique relationship between our two variables, and that's what we are looking for when we are doing these inverse functions. Now, as a notation for inverse functions, we actually use this f raised to the -1 exponent. So it looks like it's an exponent of -1, but that's actually our notation for the inverse function. And of course, we read it as f inverse. So yeah, just be careful that you're not actually doing any calculations with that negative exponent. It's just the notation we use for inverse functions. So let's try and see if we can establish this idea of one-to-one correspondence. So I've got 2 examples over here in your handout, and we're talking about a function that pairs the number of days since your birth with your age in years. So the idea is, can we have that unique relationship between these two variables? And it doesn't matter which one is the X, which one is the Y variable. One of them is the number of days since we were born, and the other variable is our age in years. So can we say this function will have that one-to-one correspondence? And if it is one-to-one, then, of course, we can find its inverse. So that's what they mean by, is the function invertible? So what do you think? Can we have that unique relationship between these two variables? Or is it possible that for the same Y value, we can end up with two different X values? So is this function one-to-one or not?
I don't think so, because there's 365 days in a year, so you could be it could be a varying amount of days since your birth, but you'd be the same year old.
Yeah, exactly. Very nice, Noah. So yeah, because think about it, two people can be the same age. Let's say they're, 21 years old, but unless they're born on the same day, same month, same date, they're not going to have the same number of days since they were born, because somebody could be born in March, somebody could be born in August, but both of those people can still be 21 years old. So you can see how the number of days would be different, but they would have the same age in years. So we actually do not have one-to-one correspondence in this first example. So since this function is not one-to-one, basically you cannot find its inverse. So we would say it's not invertible. And not invertible basically means you cannot find its inverse. Okay? So for this second example, they're still kind of using this whole idea of number of days, but this time the function is saying it's pairing the number of days, and that's for, depositing $100 at 6% interest, which is being compounded daily, and pairing them with the amount of interest. So when we're talking about compounded daily, that means your interest is calculated on a daily basis. If we say compounded monthly, that means the interest is calculated once a month. And so basically here, the idea is, if you take the number of days that we deposit this $100 into a 6%, interest earning account, and the amount of interest we are calculating, will we have that unique relationship between our two variables? Or like you saw in the first example, is it going to be that for the same Y value, we are going to end up with two different X values, or, multiple different X values? So can we say this function is one-to-one or not? Well, think about this. The number of days that we're leaving this money in this account and the amount of interest you are going to earn. So is it possible that, let's say, if you earned, $10 in interest, will it be $10 for 2 different days, or will it be $10 for this day, the next day that number will change? Or for the same number of days, so let's say we've left the money in there for 90 days. So for the same 90 days, are you going to have 2 different dollar amounts on the interest this account earned?
Since it's compounded daily, that it changes every day, so it would not be the same.
Yeah, very nice. Exactly. And that's the crucial part over here. Because they are telling us our interest is compounded daily, which means you are earning interest every day. So if you look at the account today, you know, that amount of interest is going to be different if you were to go back and look at the account tomorrow, right? Because it will earn some interest up until today, whatever that number is, and then tomorrow, because it's earning interest daily, that number will go up slightly, right? So that number will change. So in this case, you will have that unique relationship between your X and Y variable. So we will say this is a one-to-one function, which means we are able to find its inverse. So we can say, yes, our function is invertible. So you have to look for these relationships. Oh, okay, Jacob, sorry about that. All right, guys, so you can basically try and identify if you have an invertible function or not by basically following this definition that for the same y coordinate, we should not have different x coordinates. Graphically, basically, you can also use what we call as the vertical line test, you know, which is of course very similar to that, horizontal line test, which is very similar to our vertical line test when we were talking about functions in section 2.1. So it's the same idea. If the horizontal line crosses your function at more than one place on the function, you are not going to be able to find its inverse. So you can see for the absolute value function, we actually do not have an inverse function. But then you look at this x to the third power function over here, and the horizontal line only crosses at one point. So we know we can find the inverse for this function, and the inverse for x to the third power, you know, of course, is going to be cube root of x, because the cube root will undo what the cube function does. So that's kind of how you would use the horizontal line test. So let's take a look at some examples here from our homework. So let's start with this guy over here. So what do you think? Is this function going to be one-to-one or not one-to-one?
No, it is not one-to-one.
Yeah, because it's going to fail that horizontal line test, right? If we just draw a horizontal line through that, you can see it's going to cross at 2 points. So definitely this function is not one-to-one. Okay. What do we think about this guy here?
Yes.
Yeah, exactly. Because again, it's going to pass your horizontal line test. You can see it only crosses at 1 point. So, you know, of course, visually, it definitely can help you out. But remember, we don't always try and depend on these functions visually. We want to make sure, you know, we can do this algebraically also without having to use a graph. So let's take a look at this example over here. And you have something similar to this in your video lecture also for this, but I wanted to make sure you guys will be able to do an example like this. So you should be able to see, you know, something like this. This is very similar to the example we're getting ready to do. So algebraically, how can we determine if our function is one-to-one or not? So remember, the definition is for the same y coordinate, we cannot have different x coordinates. So what we actually do when we're trying to show these algebraically, if we have a one-to-one function or not. Okay, Jacob, that's really good. Thank you for letting me know. So what we actually do is we start out by saying, you know, what if, let's say we are pretending that we are using two different x values. So you actually write these guys as r of x1 equals to r of x2. So we're actually starting out by pretending like we have two different x values, and our goal is to try and show that they are actually the same x value. So we're not using numbers, we're just using x sub 1 and x sub 2. And our goal is to try and show that x1 and x2 are actually the same number. So we have to show that they are equal to each other. So if we can show that, then basically the idea is we are saying our function is 1-to-1. We do not have two different x values for the same y value. And so what we're going to do is on each side, we are going to replace our x values by x1 and x2. So wherever you see x in that original function is where we are going to replace it with x1 and x2. So on the right-hand side, sorry, left-hand side where I have r of x1, that will become 4 minus x1 divided by x1 minus 6. And then we're going to do the same thing on the right-hand side, r of x2. So that will be 4 minus x2 divided by x2 minus 6. So you're taking your function and you're setting it equal to each other. x1 values on the left-hand side, x2 values on the right-hand side. And again, we'll go through our calculation process, and the goal is to show x1 is equal to x2. So after you set this up, the first thing we're actually going to do is cross multiplication to try and simplify these. So that means on the left-hand side, we are multiplying 4 minus x1 with x2 minus 6. That's our cross multiplication. On the right-hand side, we are multiplying 4 minus x2 with x1 minus 6. Okay, and then, of course, since you are multiplying two binomial terms on each side, we will need to do FOIL. So when we do this, let's see, we are multiplying 4 minus x1 with x2 minus 6. So when we're doing FOIL, that means you multiply the first terms together. So that's 4 times x2. We multiply the outer terms together. So that's 4 times negative 6, which would be negative 24. The inner terms is going to be negative x1 times x2. So that's just x1, x2 over here. And then our last terms will be negative times negative is positive, and then 6 times x1. Okay, so that's what you will get when you multiply the left-hand side of our equation. And we're going to go ahead and multiply the right-hand side also. So right-hand side, we have 4 minus x2 multiplied with x1 minus 6. Okay, so same thing. Multiply your first terms, which will be 4 times x1. Multiplying our outside terms will be, again, 4 times negative 6 will give us negative 24. For the inside terms, we are again multiplying negative x2 with x1. So you can just write that as negative x1, x2. And then our last terms, we are multiplying negative times negative, which will become positive, 6 times x2. Okay, so both, products, both FOIL terms look very similar, but, obviously the x1, x2 values will keep changing based on what we had. So let's bring that back to our equation over here. So on the left-hand side, we have 4x2 minus 24 minus x1, x2 plus 6 times x1. On the right-hand side, we have 4x1 minus 24 minus x1, x2, and again plus 6x2. So FOIL each side, and now what are you going to do? What do we need to do to simplify this further?
Add like terms together.
Yeah, very nice, Michelle. Exactly. We want to try and bring those like terms together. So I've got 24 on both sides. So let's go ahead and combine them so we can go ahead and add 24 on both sides. for that matter, your x1, x2 term is also common on both sides. So we can go ahead and add that x1, x2 term also. And you can see when we try to add these guys will of course end up canceling each other out, which is good, right? Because it helps us simplify these terms further. So once you have that, you know, then we can see what's left behind. So on the left-hand side, we have 4x2 plus 6x1. On the right-hand side, we have 4x1 plus 6x2. And we still need to do the same thing. We still want to get our like terms together. So you want to get the x1 terms on one side, x2 terms on the other side. So how about we go ahead and subtract this 4x2, move it to the right-hand side, and we'll subtract the 4x1 and move it to the left-hand side. So these guys will cancel out, and then when we add these together, we will end up getting 4 minus 6 would be 2, so we will have 2x1 equals 2x2. Now, what do you think the very last thing we need to do here to clean this up?
Divide by 2.
Yeah, just get rid of those 2's. So divide both sides by 2, and you can see we were hoping to show x1 is equal to x2, and that's exactly what we have over here. x1 equals x2. So when we can show this, we can basically say our function is 1-to-1, which also means we can find the inverse for this function. So our function is invertible. So that's basically the goal behind this process of trying to show algebraically if our function is 1-to-1 or not. And so of course you select the first option and we should be good to go. Okay, did anybody have a question on this example? So take it slow, you know, take it step by step, because if any slight mistake we make in the intermediate steps, we know our final answer will not be accurate. So just have to go slow when you're trying to break these kind of problems down. And again, like I said, I do have these examples in your handout and your video lectures also, so you can always go back and reference those also. So this was again just to see if our function was 1-to-1 or not. Now, let's take a look at our next example here. Okay, so this one is giving us a set of ordered pairs, and they first want us to find out if the function is invertible or not. If it is, then we can find the inverse. So since you can see that they're giving to us a set of ordered pairs, we have to basically identify, and again, looking at our definition, we want to basically identify that for the same y coordinate, you do not have different x coordinates. So keeping that definition in mind, is this function 1-to-1? Is this function invertible?
No.
No, and why is that?
So we have 2 1s with different x coordinates.
Yeah, very nice. If you will actually look at these two ordered pairs over here, you can see we have the same y value, but then we have 2 different x values over here, and it definitely fails the definition of our function being 1-to-1. So since for the same y coordinate, we have different x coordinates, this function is not 1-to-1. And remember, if it's not 1-to-1, you cannot find its inverse. So not 1-to-1, which means the function is not invertible and we cannot do anything about that. Okay. All right, let's look at our next one over here. So again, you first want to check and see if this function is invertible or not, if it's 1-to-1 or not. So can we say this function is 1-to-1 or not? Okay, I'm getting a thumbs up from Teddy over there. So if you just look at the x values, you have 2, 7, sorry, y values, not x, 2, 7, and -4. Each of those are different, right? So we don't even have to worry about that repetition happening. So yes, definitely this function is 1 to 1. And if your function is 1 to 1, then you know it's invertible, which means you can find its inverse. So remember what I showed you here with the pizza example? Just by switching our x and y values, we are able to create the inverse function. So when you are given set of ordered pairs, you can do the exact same thing. Now that will not work for equations, but it definitely works for set of ordered pairs. So what do you think this inverse function will look like? So how will you write that inverse function for that original f function?
Would it just be 2, 3, 7, 1, and -4, -2?
Yeah, exactly. Very nice. Just switch those ordered pairs around. So you would have 2, 3, and then comma, let's see, 7, 1, comma again, and then -4, -2. Very nice. And that's it. That's all you have to do when you're given the set of ordered pairs. Now, you know, like I said, this would not work if we were given equations, but it definitely works with set of ordered pairs. All right, so can you tell me what f inverse of -4 will be?
Is it -2?
Yeah, very nice. So you are looking at the f inverse function, and then you're trying to find the ordered pair where your x value is -4, and you know that's of course going to be the corresponding y value. So -2 is correct. Very nice. Alrighty, and then the last part is actually asking us to use composition over here. So for this guy, you can basically see they're asking us to do a composition between the f inverse and the f function. So that would of course be f inverse on the outside and then f of -2 on the inside. So starting with f of -2, what will that answer come out to be?
-4.
Yeah, because you're going to the original f function, finding the ordered pair with -2 and looking at the y value. So -4 is the correct answer. So that means you will have f inverse on the outside and then replacing the f of -2 with -4, and then what will that end up giving us? So f inverse of -4 was what?
-2.
2.
Yeah, -2, because that's the same ordered pair you had over here. So you can see what happens here is originally we started out with the x value of -2. By the time we went through that calculation of our composition with these two functions, you actually come back with that same answer of -2. So what happens in this case is, and let me type that answer here quickly. What happens in this case actually is that when you do a composition between the original function and its inverse, let me disconnect my laptop before I lose my power. Let me go back over here. So whenever you are doing compositions with the inverse function and the original function, not here. There you are. You are actually going to end up with what we call as the identity function. So what happens is anytime you do these compositions, and basically you can see we are saying f and g are inverses of each other. So if we take the composition in either direction, you are always going to end up with x as your answer, which is actually the function y equals x, which is your identity function. So this is where, you know, whatever is the x value, you have the same number for the y value. So you always have those ordered pairs like you just saw, -2, -2, you know, -10, -10, 5, 5. So all your x and y values will always be the same. So this always happens when you do the composition between the original function and its inverse, you end up getting this identity function. So whichever x value you started out with, after you complete the composition, it's the same answer you are going to get for your y value. Okay, so this was a nice little example to kind of show us, you know, what happens when you do the composition between these two functions. Now let's take a look at this guy over here, but this one is actually giving us the graph of two functions and asking us to decide if these guys are inverses of each other or not. So this line that you are seeing, the dotted line over here, this line is actually the y equals x function, because we know if the two functions are inverses of each other, you know, using that idea of the composition where we know we end up with an identity function. So what happens is if you use this diagonal line y equals x as your reference line, or think of that as a reflective surface, if our two graphs are going to be reflections of each other with respect to this line y equals x, we can actually say they are inverses of each other. The other thing you can do is, you know, pick a point on this y equals x line and try and see, you know, what the distance will be on opposite side of that point. So you can go, you know, down this way, look at this distance. You can go up this way and look at that distance. Is that distance going to be the same? And, you know, of course, that should be the same throughout our graph with that entire distance. So if the two distances are the same, then we can say, yes, they are reflections of each other. Sorry, inverses of each other. Or imagine if we fold our graph along that dotted line, will the two graphs coincide, right? Kind of like what we had talked about in symmetry. Will those two graphs overlap? So kind of looking at that, what can you say? Do you think these two graphs are inverses of each other? Yeah, I can see a lot of you nodding your head. Yeah, exactly, because they are going to be overlapping on each other. That distance from the line is the same. So this guy is definitely an inverse for the other function. Alrighty, very nice. Let's take a look at this function over here. What do you think? Noah, you're saying yes? And again, you know, use that idea of distance that I was saying. So imagine again, if we take a point over here, is this distance going to be the same as this distance over here? You can do it down over here. Is this distance going to be the same as this distance over here? Or what happens if you fold along that red line? Will our two halves coincide? So what do you guys say, yes or no?
I think it is.
You think it is? Okay. All right, let's check that. Alrighty, very nice. Now let me show you just another type of example that you can see. So I'm going to click on similar. You know, again, this guy is actually very similar to the example we just did. Let me see if it will show me a little different. Yeah, this is kind of what I was hoping to show you. So if you look at this graph over here now, so you can again see if we just pick a point on our y equals x line, and if we try to talk about the distance, you know, just go horizontally if you want. You can just talk about this distance over here, and you can see how much longer this distance is from the other side. You can actually do that kind of over here also if we just go in this direction, and if we go in, you know, this direction, which we would have to keep going. So we got that. You can again see those are not even distances. Even if you try to fold your graph along the line, the red line, you will see those two halves are not going to be coinciding with each other. So obviously you can have some graphs which will look like this guy over here, which are not going to be inverses of each other. So, you know, obviously my MATLAB is going to keep changing these graphs on you. So just be, you know, mindful when you're trying to figure out if they are inverses of each other or not. So let's take a look at this example over here actually to try and see when our equations are given to us in the equation form, how do we find our inverse? Now, you know, with the set of ordered pairs, we could just switch the x and y values and we were able to come up with our inverse function. But when they're given to us as equations, obviously our process is going to be a little bit different. So one thing I did want to point out before we get into that example is, trying to find my statement over here. Yes, this guy will do. So basically what happens is because we are interchanging our x and y values, the domain of the original f function actually ends up becoming the range of the inverse function, and the range of the original function will end up becoming the domain of the inverse function. And you can kind of see that in this illustration over here also. So we are going to use the same idea that we need to switch our x and y values, but with the equation, our process is going to be a little bit different. So you do have these steps listed over here for how to find the inverse function. So let's try and use this idea in this example over here. So the first step is going to be, we will need to rewrite our f of x as the y variable. So you're going to write this as y equals 7x plus 5 divided by 2x plus 3. And this is what we call as the switch and solve method. Okay, so first step is replace the f of x with the y variable. Now this is where the switch part is going to happen. So what we're going to do is interchange the places of our x and y variables. So where you have y, that will become x, and where you have x, that will become the y variable. So this is the switch that's happening. So now we should have x equals 7y plus 5 over 2y plus 3. The solve is where now we have to try and get the y by itself and move everything else to the other side. So the switch was, you know, interchanging our x and y variables. The solve is going to be now try and bring the two y values together because we do have y on the numerator and denominator. And then, you know, we want to isolate the y. So the first thing here we need to do is actually get rid of that denominator. So we'll go ahead and multiply both sides of our equation by that denominator of 2y plus 3. So both sides multiply by 2y plus 3. Now on the right hand side, you know, of course, what will happen is the 2y plus 3 will cancel each other out. So we should be left with x times the quantity 2y plus 3 on the left hand side. On the right hand side, of course, we cancel the denominator out. So you should be left with just 7y plus 5. Okay. Again, guys, remember our ultimate goal is to get the y terms together and move everything else to the other side. So to achieve that, the first thing we're going to do is take this x, distribute it inside our parentheses. So that will end up giving us, let's see, 2 times xy for that first term plus 3 times x. And then, of course, we still have 7y plus 5 on the other side. You've got one y term on the left-hand side, one y term on the right-hand side. So bring the y terms together on one side. So what I'm actually going to do is get rid of this 3x, move it to the right-hand side. Okay, so get rid of that over here. Now, to bring the y terms on the same side, I'm going to go ahead and subtract my 7y and bring it onto the left-hand side. So you can basically see we bringing the y terms to the left and the non-y terms to the right-hand side. All right, let's see now what we can do. So you've got on the left-hand side, let's see, what do we have? 2xy minus 7y. On the right-hand side, we should have negative 3x plus 5. Right, so the y terms are now on the left-hand side. The non-y terms are on the right-hand side. We still have y distributed between two different terms. We still need to find a way to bring those y terms together. So since both of these terms have that y in common, you can bring the y outside as your greatest common factor, which means if we factor out that y and bring it on the outside, on the inside you would be left with 2x from the first term minus 7 from the second term. And then, of course, right-hand side will still stay the same. So we should still have our minus 3x plus 5. And, you know, we're almost there. What do you think we can do to get the y by itself?
Multiply both sides by y.
No, we don't want to do that.
Divide both sides by y.
Divide by y. Or what else could we do if we're trying to isolate the y, get the y by itself?
Divide both sides by 2x minus 7.
Yeah, because we want to isolate the y, right? Because if we ended up actually dividing by y, that means you're putting it back in with the other terms. But if you actually just get rid of the 2x minus 7, divide that, then we get y by itself. Tessa, does that make sense? Yeah? Okay. So we end up dividing both sides by the parentheses 2x minus 7. You know, of course, that will cancel out on the left-hand side, getting that y by itself. And now you have minus 3x plus 5 over 2x minus 7. And, you know, of course, you can replace that y with your inverse notation now. So this guy will be our inverse function. And you know, there's actually a process where you can use a mental method to try and find your inverse function, and I will show you that with some of the other examples. For this particular example, I do not recommend using the mental method because it does not normally work out the way you think it's going to. So for this type of example, I definitely recommend using the switch and solve method. So let's go ahead and plug that answer into our function over here. So that's negative 3x plus 5 on the numerator. And we're dividing this by 2x minus 7 on the denominator. So let's check that. And of course, you can see that's kind of how these switch and solve methods work out to be. Questions on this one, guys? Again, it's a little bit of a slow process. We have to be careful, you know, when we are going through this math, but as long as you can be a little patient with this, you know, these calculations definitely work out. So that's going to be your process by using the switch and solve method to try and find our inverse function. You've got, you know, another example over here to find the inverse. So again, I'll show you with the switch and solve method, but then I'll also show you how the mental method works for this. So before I show you that, I want to give you guys a chance to try and work through this example. So again, you know, start by replacing your f of x with the y variable. So you would end up with y equals cube root of x minus 8. Okay, so once you replace the f of x with the y variable, then basically remember that's where we do the switch. So you switch your x and y variables. After you make the switch happen, you will need to get rid of the cube root. And once you get rid of the cube root, then you want to get the y by itself. So I'll give you guys about a minute to work on this. Don't send your answer in just yet. Just have your answer ready. And when I ask you to, you can send it in. So just let me see what kind of answers you guys are coming up with. All right, guys, go ahead, send your answer in. Let me see, Teddy, you've got x cubed plus 8. Noah, Allison, x cubed plus 8. Raymond, same thing, x cubed plus 8. Marcia, x cubed plus 8. Chloe, alrighty. Michelle, okay, Tessa. Okay, looks like that's what most of you guys have. Yeah, Cassiano. So, like I was telling you, yeah, you do the switch. So get the x on the outside. The y will go on the inside. Kalia, Daisy, you guys also have the same answer. Now, what's going to happen over here is, because again, our goal is to get that y by itself. So as I was mentioning, you would need to get the cube root taken care of. So to get rid of the cube root, you know, of course, we would have to raise both sides of our equation to the third power. So that would help us cancel out the cube root on the right-hand side. So you would end up with x cubed on the left, y minus 8 on the right. And then to get that y by itself, you know, of course, we would go ahead and add that 8 to both sides, and you would end up with x cubed plus 8 equals y. And, you know, of course, then replace that with your inverse notation. And we end up getting x cubed plus 8 as our inverse function. So, of course, we can go ahead and check that, but let me show you the mental method before I do that. If you wanted to try and solve this, what we call as, you know, mentally, which of course means you don't have to use the switch and solve method. So if you look at our original function, you know, we have y equals cube root of x minus 8. So here the idea is, if I give you x as, you know, 0, let's say we give you x equals 0. What's the first step you are going to do? Are you going to subtract 8 first, or are you going to do the cube root first? So if x was 0 or, you know, 1 or whatever number you have for x, what calculation would you do first?
Would you do the cube root?
think about that. If I give you the answer for x something, let's say x equals, and I'll just use 0. If you have cube root x is 0 and you have -8, so again, would we do 0 minus 8 first, or would you do cube root of 0 first?
Zero minus 8.
Yeah, we would do the subtraction first, right? So the idea is whatever the x number is, the number doesn't matter. The first thing we would do is subtract 8 from that number, and then whatever answer we got from that, we would end up taking a cube root on top of that answer. So the subtraction happens first, then the cube root. So what happens in the mental method when you're trying to find your inverse is you actually have to go in the reverse direction, and you have to do the opposite operation. So since we did cube root last, with our inverse function, for our, again, we just use x as our variable, but since the cube root happened last in the inverse function, the cube, which is the opposite operation, has to happen first. And then since the subtraction happened first, the opposite of that would be addition. The addition has to happen last. So remember, in the mental process, the idea is you have to go in the reverse order and then do the opposite operation. And of course, you will see this is going to be the same as our switch and solve method answer that you came up with. So that's kind of how that mental process of finding the inverse function works. So that's going to be x raised to the third power plus 8. And, you know, of course, you will see that's what our answer should be. So you do have some calculations in your handout where, you know, I'm giving you problems to work with the mental method. But just keep in mind, for this type of example, use the switch and solve method, because your mental method, every time I have tried to do it, it hasn't worked out. So unless you're really confident, I do not recommend using the mental method over here. So you've got examples over here at the end of helping you find inverse functions mentally. So you can practice with this. You can look at the answers for that in, you know, the video lectures. Now, this next set of example is, you know, actually coming back to this idea of doing compositions with our inverse functions. And that's a great way to check and see if the two functions are actually inverses of one another or not. So by doing these compositions, again, we are trying to see, are we going to get that identity function as our answer? So will we get x as our answer when we try and do these compositions? So that's what this guy is asking us to do, is to try and determine if f and g are inverses of each other or not. So what we have to do here is, let's simplify this and see what we come up with. So we'll start with the f of g of x first. So that's f on the outside, the g function on the inside. So the g function is 7 divided by x plus 6. So you're actually going to plug this into our f function. So that means wherever you see the x variable, you have to replace that x variable with, you know, the g of x function, 7 over x plus 6. So our f function is 7 on the numerator, x minus 6 on the denominator, but instead of x, we're replacing it with the g function, so that would be 7 divided by x plus 6 in here. And then, you know, of course, our goal is to try and simplify this. So if we just write this out, you will have 7 on the numerator, 7 over x plus 6 minus 6 on the denominator. So as you can see, those plus 6 and minus 6 will end up canceling each other out, leaving us behind with 7 on the numerator, and then the fraction 7 over x in the denominator. Now this is the same thing as saying 7 being divided by the fraction 7 over x. So to try and simplify this, if you remember when, you know, we talk about dividing by fractions, we keep the first value as it is, we change division to multiplication and then invert our second fraction. So you can use that same concept over here, keep the numerator as it is, change division to multiplication, and invert your bottom fraction. So that becomes x over 7. You have 7 in the numerator, 7 in the denominator. They will cancel each other out. And as you can see in this composition, we are getting x as our answer. You know, so that's a really good sign that we got x over here. So then for this guy, you know, of course you are saying this equals x. Alrighty, now they're of course asking us to do it in the reverse order. So now we are doing g of f of x. And if it works out in this case also, then, you know, of course we can say we have inverse functions for f and g. So g is now going to be the outside function. F is going to be the inside function. So that means this guy is now going to go on the inside. So 7 divided by x minus 6. And that means in the g function, wherever you're seeing an x, you're going to be replacing it with this f function. So that is going to be, let's see, g is 7 divided by x plus 6. And instead of x, we are going to have 7 over x minus 6. So again, guys, since we have this fraction over here, 7 divided by this fraction 7 over x minus 6, right? We're going to do the same thing we did here on the right-hand side, and you are going to have 7 multiplied by, invert that fraction, so x minus 6 on the top, 7 on the bottom, and then we still have this plus 6 at the end. And again, by inverting that second fraction, you can see our 7 and 7 will cancel each other out. We will be left behind with x minus 6 and then the plus 6 at the end. And now we can again cancel out the positive 6, negative 6. And even in the reverse direction for our composition, we are still actually coming up with x as the answer. So once you get that x here again, and we're getting x and x for both forms of our composition, then that definitely tells us that we are looking at inverse function, because that's exactly what this theorem over here is talking about. If both directions give you x and x as the answer, then we know for sure that we are looking at inverse functions for one another's. Then of course you're going with option C over here. These functions are inverses of each other. Okay, so that's basically what they're having us do in this last example over here. So questions on this one, guys? Alrighty. One other thing that I wanted to talk about with these inverse functions is actually right over here, where we are actually looking at the graphs of these functions. So let me kind of show you this example over here, number 17. What happened? So right now our original function is f of x equals, square root of x plus 2. So if you try to find its inverse function, hold on a second. Now you can use the switch and solve method, or you can use, the mental method. So you can see in this function, if we take our value of x, we would first need to add the 2 to, simplify that. And then whatever answer you get after adding 2, that we would end up taking the square root function of that. So remember, in the mental method, you have to go in the reverse order and do the opposite operation. So if you did that, our inverse function would come out to be, with the x variable, since we did the square root last, we would have to do the square function first. And then since we added the 2 first, you know, we would have to subtract the 2 last. So if we try to graph this inverse function, let's look at our Desmos over here. So our inverse function is x squared minus 2. Now, if you look at this function, you can see it's going to fail the horizontal line test, right? Because the horizontal line will cross this at 2 different points. So how is it possible that our inverse function is coming out to be a function that's not even 1-to-1? Because we know if the function is not 1-to-1, we cannot find its inverse. So what happens over here is you actually have to use the idea of domain and range. So let's talk about the domain for the original f of x function over here. So what do you think the domain for our f of x function is going to be? Square root of x plus 2. What x values are okay to use in that square root of x plus 2 function?
Could you say that last question one more time?
What would be the domain for this f of x function? What x values are okay to use in that function?
Would it real numbers? Oh, no, mind.
Eddie, would you say that again, please?
I said, would it be all real numbers? But then I realized that it's not with the 2.
Okay, yeah, because Dalton has anything greater than -2. And actually, Dalton, you can include -2 also in there, because when we use -2 for our x value, -2 plus 2 will become 0, and square root of 0 will be 0. So you can use -2 to infinity. But if you use numbers smaller than -2, then remember that's when we'll get into negatives inside of our square root, which will lead to imaginary numbers, and we don't want that. Which also tells us, since -2 is going to be the smallest value for the x, that means for our y value, you know, of course, the smallest number will be 0, because you will be going from 0 to infinity. So if you remember, because of that interchanging of our x and y variables, that means the domain of our inverse function, so f inverse of x, is actually going to be the range of the original function, which means the domain is going to be now from 0 to infinity, including 0. And the range of the inverse function is going to be the domain of the original function, which is going to go from -2 to infinity. So let me show you on the graph what happens when we try and graph both of these functions together. So let's do, for our second function, the square root of x plus 2. There's our square root of x plus 2. So you can see, if we can ignore this left-hand side of our parabola over here, so just ignoring this whole left part, because we know the domain of our original function was from, you know, -2 to infinity. This is the domain of the original f of x function, going from -2 to infinity, and the range for the original f of x function was 0 to infinity. And this range of the original function, of course, becomes the domain of our inverse function. So you can see, for the inverse function, which is this parabola, we are starting at 0 and going towards positive infinity. So we are able to verify that for the range of the inverse function, you can see it's starting at -2 on the y-axis, and it's going up to positive infinity. And again, if you imagine that y equals x line as our line of reflection, you will see how those two graphs will end up becoming reflections of each other as long as we do not use that left-hand side of our parabola for the x squared minus 2 function. So what happens sometimes is, for examples like these, we actually have to restrict our domain. So instead of using the entire domain for the x squared minus 2 function, we are saying only go from 0 to infinity, and we are able to find its inverse. But if you were to keep the original function, you know, we would of course not be able to find an inverse for that. So by restricting our domain, we are able to create inverses. And that's actually what we're talking about here with the x squared and the square root function. So you will see we are not using the whole parabola for that x squared function. We're only going from 0 to positive infinity. So same thing's going to happen actually in this graph over here also. We will have to restrict our domain. So if you have not seen the video lecture, make sure you see this so you know exactly how to look at these you know, graphs. And then again, guys, we have these problems over here to help you find the inverse functions mentally. So again, you know, use that for practice. Now, even though 2.6 is not part of our required sections, you will not have homework or exam questions on 2.6. I just want you to be aware that 2.6, we are making the assumption that you are comfortable with variation and you have done variation in your previous class. So even though we're not using variation in this class, you know, whichever one you end up going to, the next one might be something that you might need it. So you do have this handout in your D2L. We talk about the different types of variation. So you can see here, we're looking at the direct variation, and direct variation basically means if one quantity is increasing, the other one also increases. If one quantity decreases, the other one will also decrease. So if you think about that pizza example we saw in the last section, the more toppings you got, the more money you had to pay, right? The less toppings you get, the less money you have to pay. So both quantities either go up or both quantities go down. That happens in direct variation. You can also have inverse variation. So as the name suggests, with inverse variation, the idea is one quantity goes up, but the other one goes down. Or if the second quantity is going up, that means the first quantity was going down. And you know, a great example for that is speed versus time. So if you think about it, and we always do that, right? If we're running late, we think if we drive faster, we'll get there faster. Maybe not, you know, it doesn't work out every time. But just with thinking about, you know, a Boeing 747 plane against a Concorde plane. So Concorde, you know, had a speed almost double that of a Boeing 747. So the idea was, you know, if you were traveling long distances, you should get there in less amount of time if you were taking a Concorde, which would be a faster plane. So faster speed, less time, right? Or if we did the Boeing 747, which is a slower speed, that means we would need more time to get to our destination. So this is the inverse variation. You can also have what we call as joint variation, which I kind of think of joint variation more as direct variation. The only difference is you have multiple different variables instead of just two. So basically the idea is both x and z variables will be going up if y is going up. And, you know, again, both x and z would be going down if y was going down. But basically the idea is all the quantities would be growing or all the quantities would be going down. So joint variation is just by bringing in more variables, but the process is still very similar to your direct variation, you know, as far as the calculation goes. A combined variation, they don't actually give you a distinct formula over here, but combined variation actually means you are combining both direct and inverse variation together. So that actually means if y is going up, then the x variable is also going up. but that means the z variable is going down, which means two of the variables would grow, but then one would, decrease. So x and y, because they are in the direct variation format, they are growing, but z with respect to y is in the inverse variation setup. So if y goes up, z would be going down. So your combined variation is basically combining direct and inverse together. So it's actually really interesting. But like I said, for AIMS, because you have seen these in other classes, we don't really talk about it. But if you think variation is something you will need going forward, then I would say, go ahead and take a look at this handout in your D2L. And, of course, you can use it as reference anytime that you like, but you will have no questions, no homework on section 2.6. So don't worry about that. This was just so you know that this is there for you if you need to look at it. So before I dismiss you guys, did you have any question on the exam or what we just did with 2.4, 2.5? Before we go and take our exam for chapter 2 on Thursday? Okay, if you think of anything, I have office hours today, I have office hours tomorrow, so feel free to reach out to me if you need help, and we can definitely go over anything you might have a question about. So just make sure you get all of your homework and quiz for chapter 2 completed, and then I will see you guys on Thursday morning. So be careful, everyone, stay safe, and I will see you on Thursday morning. Take care. Bye, guys.
Bye.
Bye, take care. Did you guys have any question for me?